Over the summer 2015 question 5 cash question, you very likely will not see a question that's as difficult as this one on your midterm, maybe the final. The main reason why is because, in my experience, when we gave this question, it was just too hard for way too many students. No student got more than 20% of it correct, so it's actually really hard to gauge how well students learn about caches during the semester if there's just a question that's too difficult for even one student to solve. However, it's good that you're curious about this question, because if you can do this question, you'll probably be quite successful in whatever shows up on the midterm. So I'll just go over it right now. So we're given some information about two different caches, and one way I like to first start trying to solve a cache question is to observe the information that's given to me. So we're told that we're given caches within a 32-bit physical address space. So that's some pretty important information right there. And we're given two different routes. We have one direct map cache, and we have one two-way set associative with LRU replacement policy. And we're also given the cache sizes along with the block sizes. And this is just standard write back and write allocate. So what this means is that if we miss, we load the block of memory into the cache, and at the same time, when we write, instead of writing to memory, we write to the cache block, and that value gets updated in memory once that cache block is evicted and replaced with another block in memory that maps to the same location in the cache. So an important place to start is to observe that 4 kibibytes is equal to 2 to the 12 bytes, and 512 bytes is equal to 2 to the 9. So just make sure you understand your powers of 2 and you remember your IC prefixes. So if we look at this, well, we can determine pretty much what the parameters of our tag index offset fields are. So we know that the sum of these is going to be 32 bits. So if we observe properly, we can determine that the offset, it's just going to be 9 bits per. And the reason why is because that's just the block size. So we need 2 to the 9 bytes within each block. Well, we need 9 bits for the offset. For the index, well, for direct map, we know that that's just going to be equivalent to 2 to the 12 divided by 2 to the 9, which is 2 to the 3. So log base 2 of that, well, that will be 3. An easy way, if you ever forget about how to get the index bits, well, an easy way to remember how to solve that is if you think of the direct map cache as just a rectangle. You know that the total area of data, the data it can hold, is 2 to the 12. We know that the width is 2 to the 9, so that means that the height of this rectangle has to be 2 to the 3. So that's where we get our 3 bits for the index. So we know that since the tag plus index plus offset, well, that is equivalent to 32 bits because this is a 32-bit address space. Well, 32 minus 3 minus 9, that's just going to be 20. So we need 20 tag bits. And so for two-way set associative, it's a little bit different, because the way two-way associative works is that instead of just one single rectangle or one single cache, we now have two different ways that data can go in. You know, if you load in a block, it could go this way or that way, hence the two ways. So we know that for both of these ways, the block size is going to be 2 to the 9. And we know that the total area of this whole space is 2 to the 12. So, well, if you think about this, we have to have a height of each rectangle such that if you multiply the area of this mini rectangle right here, I should probably use a different color. If you multiply the block size by the height of this rectangle, well, if you multiply that by 2, because we have two different cache, or two different ways for our cache, then that has to be equivalent to 2 to the 12. So we know that this is going to be 2 to the 2 because 2 to the 2 times 2 to the 9 times 2 to the 1 because there are two ways. Well, that's just going to be 2 to the 12. So we know that we need 2 index bits as opposed to 3 in this scenario. And what that means is, well, since we have one less bit in the index and the number of offset bits stays the same, we just need one extra bit for the tag bits such that this equals to 32 bits. And if we check the answers, that should be correct. I'm just going to make sure. And yes, that indeed is the correct answer. All right, so moving on to the next part of the question. Well, we're asked what is the hit rate for each cache if we run only loop 1? Okay, so make sure that you keep track of this. It says only loop 1. And we're given this really helpful hint. They're both the same. So it asks us what type of misses we get. Well, you know that when you load up a program, we're not given any information that the data needed for this is preloaded. So right off the bat, hopefully you're able to determine that these are going to be compulsory misses, if any, because we haven't seen any of the tags for any of the blocks that we need in memory. So I'll leave that a little bit for later, but for now, this is how we'll start the question. So we're told we're given a double array right here, double array of size, double array size. And we know that the double array size, well, what is this? This is 2 to the 10 times 2, that's 2 to the 11. So 2 to the 11 elements. Now, something to keep in mind, though, and a lot of students always make this mistake, is that we have 2 to the 11 elements, but how many bytes is each element? Well, each element is a double, and we're told that doubles are 8 bytes. So we need to multiply this by power of 3, or 2 to the power of 3, and that gets us 2 to the 14. So we know right here that the number of bytes that our double array takes up is 2 to the 14 bytes. And that's something important to keep in mind because we know that our cache size is given to us with a size in the units of bytes. So going back to loop 1, well, if you look at this, it's just a basic iteration through each element. We go from element 0 to the end of the double array, and we only increase by one element. So if you look at that, well, we're just pretty much looking at every element of the array, and we're assigning it to whatever index value it is. So double array 0 is going to be 0, double array 1 is going to be 1, double array 2 is going to be 2. And if you think about this, well, we're just iterating through each element in the double array. So if we look at our direct map cache, well, if you remember, there were 2 to the 3 rows, so there are 8 rows. And the block size is 2 to the 9 bytes. Well, what happens is that, let me see if I could change this color. So what happens is that we try to access the first element right here. So we try to access this first element right here, element 0, if we look at just the first block, and that's a miss. It's a compulsory miss because we've never seen this block of data before. So we have one miss, but if you think about, because we're moving sequentially, we're incrementing just by +1. So we move on from 0 to the next element, which is 1. That will be a hit. And element 2, that will be a hit 2. And so on till the end of the block. And this repeats itself for each and every block because we've never seen any of the data before. None of the data is loaded into the cache already. So, whatever we get as a hit rate for this one block, we know that we can replicate that for the whole cache. The cache hit rate is just going to be some scaled value of the hit rate of this one block. So the important step to take right now is we need to determine what the hit rate of this block is. So, well, how do we determine that? Well, we know that for the block is 2 to the 9 bytes. And we know that we're increasing by one element. So we're accessing all elements within our 2 to the 9 byte block. So now it's just a matter of determining how many elements there are within each block. So how many doubles there are. So if we take 2 to the 9 divided by 2 to the 3, that's just 2 to the 6. 2 to the 6 is 64. So we know that we have one miss right here. One miss for 64 memory accesses. So what happens is that our hit rate is going to be 64 minus 1 over 64, which is just 63 over 64. And these are compulsory misses, because we've never seen the tags for these blocks of data before. Okay, so going to question C, well, this is where things get a little bit more difficult. We're asked what is the hit rate of each cache when you execute loop 2, so just loop 2. And at the same time, we're asked to consider the worst case ordering of accesses. So if you remember from lecture, the worst case is typically something that has to do with the ping pong effect. So when you have a ping pong effect, what happens is that you try to access one block and it's not in the cache, so you load into the cache, and then you access another block that maps to the same location in the cache. So you kick out the first block and load in the next block. Well, what happens is if you try to access the first block again, well, now that overwrites, or well, it kicks out the second block, which just got loaded into the cache, and vice versa. So if you keep this going on and on, you notice that your hit rate is 0. So while looking at this question, you could properly decide, okay, the solution probably has, for the worst case ordering, probably is going to have to do with the ping pong effect. Now going back to this question, well, it's still a little bit more difficult. So I'm going to write the cache specs down again. So we have 2 to the 12 bytes for the cache, and we have 2 to the 9 block size. So 2 to the 9 bytes for a block size, 2 to the 9 bytes for a cache. And we know the double array size is 2 to the 10 times 2, that's 2 to the 11. The double array itself, well, it has 8 bytes for each element, so we have a 2 to the 14 byte array. If you remember how to do basic math, well, 2 to the 14 divided by 2 to the 12, that's 4. So we need 4 caches just to fill up this whole array. Okay, well, if we look at this, so the worst possible ordering, going off the ping pong effect that I mentioned, well, it's probably going to be we access I, we try to read I, and then we try to read 0, and then we try to write to I. Okay, and the worst possible scenario is you could have miss, miss, miss for this. So now let's try to draw our cache. If you remember, it's 2 to the 9 block size. We have 8 rows, 2 to 3 rows, because I'll try to write up the cache specs again. So if you remember, we calculated 20 for the tag, 3, 9, 9, 2, and 21. So for this first block we try to access, we access element 0, so we have a miss there, and we try to read element 0. Well, notice that it's already in the block, so that's a hit. And then we try to write to element 0, well, that's a hit again. So we have this one miss, hit, hit. Now if we try to access element 8, because notice, this is really important to observe, we're taking a stride of 8. So when we access element 8, well, notice it's already in the cache, so it's a hit. We try to read 0, hit. Try to write to 8, the product of those two values we just read, and that is a hit as well. So if we repeat this for all the other indices, 16 and then 24 and so on, well, we notice that we have one miss and then a bunch of hits. So, I probably should have calculated this beforehand. Well, how many elements are we trying to access in one block? Well, we know that one block is 2 to the 9 bytes. How many doubles are there in that? Well, 2 to the 9 divided by 2 to the 3, that's 2 to the 6. So there are 2 to the 6 elements here. And also you have to keep in mind, well, we're taking a step size of 8, which is 2 to the 3. So 2 to the 6 divided by 2 to the 3, that is 2 to the 3. So we're accessing 2 to the 3 elements per block. And how many memory accesses are being performed for each element access? Well, we have 3 memory operations. So for one block, we know that there are 24 total memory accesses. And based on the pattern we're observing for this first block right here, we have 1 miss and 23 hits. So our hit rate for that first block is 23 out of 24. Okay, so this is just for that first block. And remember that actually the first block of 1 cache size worth of data. And we know that the entire array requires 4 cache sizes worth of data to hold the array. Yeah. So we know that for the next element we try to access, what will that be? That's going to be roughly 2 to the 6 plus 0, because there are 2 to the 6 elements, 2 to the 6 doubles in one block. So when we try to access 2 to the 6, well, we get a miss there, and then we try to read element 0. Well, notice that's already in the cache, so that's a hit. Then we try to write to 2 to the 6, that's a hit. If we try to access element 2 to the 6 plus 8, so I don't have room. So once we try to access the next element, well, that's going to be hit because it's already, the block that holds that data is already in the cache, and then we access element 0 because we have to read that, that's a hit. We try to write the product to this value, that's a hit. So if you look at this, well, it's also going to have a hit rate of 23 out of 24. And, if you understand math and patterns, well, you could probably see, oh, okay, for the rest of this cache, for these 8 rows right here, we're going to have 23 over 24 as our hit rate. So if you think about the cache, well, there are 8 rows per cache, and we know that we need 4 cache sizes worth of data to hold the entire array. So of those 30, so that's equivalent to 4 times 2 to the 3. That's 4 times 8, 32. So we're accessing 32 blocks of data. Well, of those 32 blocks of data, 8 of them will have the hit rate that we just observed here of 23 over 24. I'm going to try to write that a bit smaller. We're going to have a hit rate of 23 over 24. This is going to be very messy. I apologize for that. So we know that that's just for the first quarter of our, what is happening? Technical difficulties. Okay, so we know that that's for the first quarter of our cache. So, well, let's look at the other quarters of the cache. So, 4 minus 1, that's 3. So we have 3 quarters left to go. Well, for one block, what happens is that, remember, we're trying to read I, and then we read 0, and then write I. So if you remember the state of our cache when we finished that first quarter, we had 0 there at the very end. And now when we're moving on to the second quarter, we're going to read the element I, which maps to the same location. So what happens is that we have to read I, so we get a miss, and then we have to read 0, but we just overwrote the block that had 0 in it with I. So we now need to load back in 0. So eraser is too large. So we now have to load back in 0. All right. I'm just going to use a different color. So we now have to load in 0. And notice that overwrites the block that has I in it. So that's a miss. And then, well, what happens when we want to overwrite that with I? Well, that's a miss again. So notice we have 3 misses, right? Now when we try to access, element I plus 8, what happens there? Well, notice that I is currently in that block, and I plus 8 is also in the same block. So that's actually a hit the first time. It only gets difficult, though, once we try to access element 0. So when we try to access element 0, we'll notice that that's not in the block. So we overwrite this block with the block that has element 0. That's a miss. Now we try to write to I plus 8 again. Or, well, we try to access I plus 8 again, and this time we're writing. Well, notice I plus 8, it's no longer there. We just loaded in the 0 block. So what happens is, now we have to replace the 0 block with a block that has I plus 8. So now we have a miss. But when we try to access I plus 16, well, that's in the same block, that's a hit. Then we try to access the block that has 0, that's a miss, and so on. So if you remember what I said earlier, we have 24 memory accesses per block. And we know that for this one block, just right here, well, for this one block, we have all misses except, oh, I should have put miss right here. All misses for all 24 accesses. So we have all misses except hits for the first memory access of each element other than the first element. So if you understand how that works out, well, that's going to be 7 over 24 as our hit rate. So at the end of that particular block, well, if you think about, what block we currently have in there, we currently have the block that had index I. So, well, what happens when we have to access element 0? Well, when we try to access the next block, let's say that our I is right here, we try to access I, and that's a miss. And then we try to read element 0, right? But remember that the block that has 0 isn't here. We have the block that held, a previous value of I, but it's not 0. So we have to reload 0 in. So I'm just going to represent that as kind of a pink block. So we reload element 0, and we have a miss again because we just had to reload that. But now what happens is we have a hit for I, because notice that it's right here. And if we try to access our new I plus 8, well, what happens there? Now we have a hit, and at the same time, we have a hit because the block that has 0 is there. And then we have a hit again. And then if we try to access I plus 16, well, notice it's already in this block, so that's a hit. Try to access element 0, that's a hit. Try to access I plus 16 to write to it, that's a hit again. So if you look at this, well, we have only 2 misses, and everything else is just going to be a hit. So for this one specific row, what happens is that we get a hit rate of 24 minus 2, that's 22 over 24. So, it's still not finished. There's still one thing that we need to consider. I apologize for my poor photoshopping skills. So, if we look back at this cache, well, the next block that we try to access, it's not going to be there. So let's say that this is our new I. So that's a miss. But then we try to read 0. Well, notice 0 is already in the cache, so that's going to be a hit. And then we try to write to I, well, that's a hit again. And then if we try to access I plus 8, we'll notice it's in the same block. So that's a hit. We read 0, hit, write to I plus 8, that's a hit. And this repeats for the remainder of those 24 accesses. So the hit rate of this block is 23 over 24. And we know that there are 8 blocks total. This is block 1, block 2. Actually, it should be 0 index, so it should really be block 1. And this should be block 0, block 2. Well, for block 0, we have a hit rate of 7 over 24. Block 1, we have a hit rate of 22 over 24. Block 2, we have a hit rate of 23 over 24. And if you go through the remainder of those 8 blocks, well, all the way through block 7, we still have a hit rate of 23 over 24. I'll leave you to do that if you don't believe me, but that's just how it is. So remember that this is for the second quarter of the array, and we had 3 quarters of the array that we had to go through. So we know that the hit rate is going to be this value plus 3 times whatever we have in this quarter, because the second, third, and fourth quarters are all going to have similar hit rates. So, well, what's the hit rate here? We have 1 over 32 so one block that has a hit rate of 7 over 24. and we have 1 over 32, which has a hit rate of 22 over 24. And we have 6 blocks, because 1, 2 all the way through 7. 6 blocks, 6 over 32 blocks with a hit rate of 23 over 24. So if you do the math properly, well, we have 8 memory accesses plus 3, that's 11, plus 3, that's going to be 14, plus 3 times 6, that's 18, plus 14, well, that's 32 total memory accesses, or 32 blocks, sorry. So that's 32 total blocks access, and each of them have these varying different hit rates. So this simplifies down to, what is it, 26 over 32 times 23 over 24 plus 3 over 32 times 7 over 24 plus 3 over 32 times 22 over 24. So, you can already see that this is a rather complicated expression. We went through a lot to solve this, which just goes to show why it's very unlikely you'll see a problem this hard, at least for the midterm. So if you remember from earlier, we had 20 for our tag bits for X, we had 3 for our index bits, 9 for our offset bits, 9 for our offset bits for Y, 2 index bits for Y, and 21 bits for tag. Well, for our two-way associative cache, we know it will look something like this. We have a block size of 2 to the 9 on both sides, and we know that each of our different ways has row sizes of 2 to the 2, which is just 4. So actually this is probably simple enough to draw out in itself. So we have 4 rows. So, if you remember, we're taking a stride by 8, and each element is 8 bytes, as you see here. So our array size, it was 2 to the 11. However, we have 2 to the 3 bytes per element, so this is going to translate to 2 to the 14 bytes for our array. So of our 2 to the 14 bytes of our array, well, what's happening is that, remember that I said this takes 4/4 of our direct map cache. So, here, well, if we think about this, we're going to need 8 of these mini caches, these different way caches, to hold our whole array. So let's start with the first access. Well, remember earlier what we decided was that the pattern for accesses is going to be you read I, read 0, and then you write to I. And the whole hope is you get a ping pong effect, so you get the worst case ordering of accesses. So, well, let's say we start at the beginning of the array. We access element 0, and, if you remember, this is assuming after we complete loop 1. Well, none of the beginning elements of the array are in the cache at the end of loop 1. And the reason why is because loop 1 is going from the beginning elements to the end elements. And since we know the array is too big to be stored in the cache, well, the last elements are going to be all that's left in the cache, not the beginning elements, which includes index 0. So, we first access index 0, and we get a miss. And then we try to read index 0, well, that's a hit. And then we try to write index 0, well, that's a hit. And then we try to access element 8, well, that's a miss. And then we try to, actually that's a hit, sorry. So we hit element 8, and then notice 0 is already there, so we hit 0, and then we hit element 8. And this repeats for all the other elements that we access. Remember that we determined that there are 3 mem accesses per element, and the number of elements we're accessing is going to be the block size divided by the size of doubles. So there are 2 to the 6 total doubles in one block. However, we're taking a stride of 2 to the 3. So that's going to be 2 to the 3 elements that we're accessing. For each of these 8 elements, there are 3 memory accesses. So there are 24 total memory accesses. Well, for this first block right there, notice we have 1 miss and then all hits. If you don't believe me, I encourage you to go through it, but the pattern's just going to keep repeating itself. So 23 over 24. And if you look at this next block, well, what happens? Well, we miss because it's not there, and then we hit, and then we hit because the exact same reasons for here, and then all the other elements will be hits because nothing overwrites this value. It's kind of the point of the two-way associativity, is that we don't get any of those unintended conflict misses. However, in this case, I'm pretty sure it would actually be capacity misses because we've already breached our capacities. But I guess the main idea is that you have nothing that conflicts with this block. We get a load in the block that has our I, and it gets to stay there. And if there's a conflict with that, we'll go over to the next way. So that's 23 over 24. And if you repeat this for all the blocks in this cache, well, it's going to be the exact same thing, 23 over 24. And when we try to access the next block after this that maps to the same block as here, well, instead of overwriting 0, it gets to go here. And the reason why is, well, because we have two-way set associative. So instead of overwriting 0, it just gets the map here because this was the least recently used. So if you haven't already identified, every single block is just going to be 23 over 24. And this repeats itself for I believe you require 8 of these mini caches of the two-way associative cache to fill up your entire array. Well, this pattern is just going to repeat itself for each block, so we know that the answer to y is just 23 over 24.